Greetings, you motivated CP chemistry students. Today we are going to chat about what we were looking for in your responses for 1.1a, particle representations of states of matter, the CFA. Alright, so this starts with some data analysis. So we've got to take a close look at the melting and boiling points of our substances and determine what state of matter they are in. Are they gas, are they a liquid, or are they a solid? Okay, and it's a simple matter of recognizing that all of these are at 298 Kelvin, as it says here and here, as about room temperature. Kelvin, by the way, is just one of the ways we measure temperature. So if room temperature is 298, we're going to look to see whether the substance's boiling point or melting point are above or below that 298. So ethanol, for example, it melts at 159 Kelvin. So 159 is way below 298. So we know that it is not a solid, excuse me. All right, so if it melts at 159 Kelvin, it's definitely not solid. However, it doesn't boil until you get to 351.5 Kelvin. So 298 is between the melting and boiling point. That would make ethanol a liquid. Okay? Now, go over to magnesium. It doesn't melt until you get 923 Kelvin. So 298 is way below that melting point, making this a solid. And nitrogen melts at 63 Kelvin, boils at 77 Kelvin. 298 is way above both of those, so that would make this a gas. Okay? So the first thing we looked for was, could you interpret the data, determine what state it's in, and then space and distribute particles according to what state it's in. So ethanol is a liquid, magnesium is solid, nitrogen is a gas. So maybe let's just start with magnesium. So magnesium, what we're looking for when we draw solids is something that keeps a definite shape and has densely packed particles. So an easy way to show a definite shape is to just make it like a rectangular solid shape. Okay? Now, we do not need to show the exact same number of particles in each of these because it's not the same substance. Okay? So we're looking for the fact that you know that solids do not take the shape of their container and they're densely packed. Ethanol is liquid. So I can show a similar number of particles if I want to for ethanol. What I need to show is, one, it does not have a definite shape. Two, they're going to be slightly more spaced apart than the solid, but not much more spaced apart. So I'm going to draw them sort of taking the shape of this container and just slightly more spread out. Okay, so the first thing we would have been looking for was, one, does the liquid, ethanol, which is our liquid, are the particles still closely together, but they don't have a definite shape. They take the shape of that container. Then lastly, for nitrogen, which is our gas, the really important thing here is gas is always spread apart to fill the container. So I'm going to represent that by just kind of evenly distributing my particles all the way throughout that container. Something like this. Okay? So we know magnesium is solid, so we're going to represent that with tightly packed particles with a definite shape. We know ethanol is a liquid, so also particles close together. A little bit not quite as tightly packed as our solid, but taking the shape of the container. Gas particles completely separate from each other, taking up the whole space of the container. Right? Now, the next thing we want to show is that all of these have the same temperature. Okay? So temperature, as you've heard in class is the average kinetic energy of the particles. Now, there's really all kinds of little nuances because it's an average. Some particles are moving faster or slower. Some are bigger and so can have the same amount of energy by moving slower. We are not going to try to get all those nuances. We just want to show the length of the arrow equals the temperature. And since they're all the same temperature, we need the arrows to be approximately the same length. So arrows represent the average kinetic energy of the particle or the temperature. Okay? So all my arrows are going to be about the same length. Okay? What we do need to have is that the arrows are going random directions. So I'll pick a few particles. I'm going to pick about that long for my arrows. Okay? And all your teacher needs to know by looking is that you intended for all those arrows to be approximately the same length. Okay? Same thing for my liquid. About the same length. Etc. Okay? Now, the one difference that's really important to us also for solids is that we want to recognize that solids are vibrating. So I'll go the same length of arrow, but we're going to give it a double pointer to indicate those particles are in fact vibrating back and forth, which is what solids do. So slightly nuanced and like that. So here's all we look for. Did you space the particles appropriately? Did you distribute them throughout the container appropriately? And did you show all the arrows approximately the same length? If it looked like you intended them to be the same length, that's fine. Don't get out a ruler and try to make that perfect. Okay. So for the next part, we have our claim, evidence, and reasoning. And so all we're trying to get you guys to recognize is that higher or lower melting and boiling points tell us a little bit of information about how strongly attracted those particles are. Okay? So, because magnesium has the highest but melting point and boiling point, we would say it has the strongest attraction. So the claim is magnesium has the strongest attraction between its particles. Okay, so again, we're looking for the substance that has the highest melting and boiling points. Okay? Now, our evidence then is magnesium melting point and boiling point are 923 Kelvin and 1364 Kelvin, which is much higher than the other substances, something like that. Okay, so what I did is I actually pulled data out of the table and related that data, I put the numbers in there and related it to the others. Okay, so we don't need to get super long-winded there. We do want to actually pull information from our table. Lots of you guys stated magnesium has a higher melting and boiling point. Depending on how generous your teacher was, they may have given you full credit or maybe partial for that. But it's always good to actually put some of the actual numbers into your evidence column. Now the reasoning, we're looking for some way of saying that higher melting point and boiling point means more energy is required to separate particles. Okay? Something like that. Lots of you guys put 2 sentences to elaborate a little bit. But that would be enough for us to be confident that, one, you can interpret the data, right? You can make sense of it in terms of particle drawings, and you can make sense of it in terms of how strongly attracted the individual particles are to each other.